So, guess what we're doing? We're starting a new chapter. This chapter is sort of interesting. Oops. That's not what I want. There we go. So this is going to be, chapter 4. This is about functions of several variables. So this is sort of like the complete opposite of what we've been doing right now, up till now. So I want to talk about what's the difference between a vector valued function versus functions of several variables. Okay, so for the vector valued function, if f is a vector valued function, it will have a single input and it will have multiple outputs. Yeah, this is 4.1. Okay, so like what do I, so like we write, so we have this little way of writing the function notation to sort of like talk about like what's going on with the function. Oops, let me spotlight it myself. There we go. Okay, so you can see here that I have f colon r to r3. So this, remember we talked about this a while ago, but I might as well remind you. This is telling you that you have a single input from the real number line, that's a scalar. But the output is a vector in R3. So as an example, you can say the vector valued function f of t is equal to, and then we can give the components. Let's just do with let's write it with I, j, and k. You could say the x component is 3t, so you'd have like 3ti plus, I don't know, t squared minus 3j plus t cubed k. Okay, right, so this is your input scalar t, and then what are you outputting? Here are your three components of your vector. Okay, so a vector valued function has an output, which is a vector. Okay, functions of several variables are like the exact opposite. So if you have a function of several variables, your function f takes as its input a vector, and then it spits out a scalar. So now I have an input. You can think of it as like inputting a vector or inputting a ordered pair or something like that. A vector slash point in the plane. And then you're outputting a scalar. Okay, so does this sort of make sense that they're like two sides of the same coin, basically? That one of these has a scalar input, vector output, and the other has like a vector input, scalar output. So like something like this, we would write it like so. So if you look at the vector value function, do you see I have f with a vector arrow over it? If you have a function of several variables, that would be written like this. F of xy equals, I don't know, 3x plus y. Okay, so what this is telling you here is that your input is this point in the plane, x comma y, or these two values, x and y. And then your output is this singular number. Notice there's no I, j, or k. Okay, so we've learned a bit about vector valued functions. We've talked about like integrating them, taking their derivatives. You can take the magnitude of them, things like that. So now we're going to start looking at calculus from the point of view of what if you have a function which has several variables as an input as opposed to a function which has several variables as an output. Okay, so in particular, what we're going to start off with is a function of two variables, x and y. So in other words, your two variables are the inputs, x and y. And you can think of these inputs as belonging to the plane. Okay, so let me draw the picture here of what happens. Okay, so you have your xy plane. Okay. And in the xy plane, we're gonna draw off a little region that we're gonna call D. Okay, so this subset of the plane, so D is a subset of the plane. In other words, a subset of R2. Okay, so all of that stuff, that's the domain of my function of two variables, f. Okay, so the idea is you choose a point right here in the domain, this point x comma y, and you can feed it into your function f. Okay, and your function f, after you feed in this point x comma y, spits out a single number z. Okay, and this single number z is a point on R1, which is the real number line. Okay, wait, I don't want green, I want white. There we go. Okay, so over here you have your domain. It is area D. And then over here you have your range, which is a subset of R. Right, because your function f, it has an input from R2 and an output in R. So this point Z is somewhere right here. Okay, so this function of several variables, it takes a point right here in the plane and it associates it with a point over here on the number line. And it does that for every single point. Like if you choose some point over here, x naught, y naught, well, if you were to go and calculate f of x naught, y naught, you would get some z naught, which would be some other point over here. Okay. Okay, questions so far? We'll do some examples here in a moment. So let's give you like a more concrete example. So example, let's let g of xy be equal to the square root of 9 minus x squared minus y squared. And what I want to do is find the domain and range. So we've got our square root of 9 minus x squared minus y squared. Okay, so we would write z equals 9 minus x squared minus y squared. Okay, so looking at this, well, what do you know about the square root function in terms of its domain? Like, how does the square root work? What are you not allowed to take the square root of? Negative numbers, right? So we know that the thing that we're taking the square root of, that needs to be greater than or equal to 0, right? If it's negative, it's not in the domain. So this has given us an equation to set up. We can, or not an equation, an inequality. We can solve this inequality to figure out what points in the plane are going to be in the domain. And you can like rewrite this. If you add an x squared and a y squared to both sides, you get that 9 is greater than all right. That doesn't make any sense. 1 second, I'm having a good brain fart. Well, I guess we could do this. If you subtract 9 from both sides, you do this. Oh, there we go. And then if I discharge the negatives, if I multiply everything by -1, what's going to happen? It's going to have to switch, right? There we go. That's the proper way to do this. Okay, so these numbers are in these. So let's put this. The xy points that satisfy this inequality are in the domain of g of xy. Now, what do we know that what does the graph of this inequality look like? So x squared plus y squared less than or equal to 9. If we were to graph that on the xy plane, what is that? Yeah, a circle of what? 3, right? Because this number, it's x squared plus y squared equals r squared. So 1, 2, 3. Let's insert a circle. There we go. So there's my circle of radius 3. So this is my domain, and any single point inside of here can be plugged into g of xy. So and in fact it includes everything in here, right? All of the points in here are included. Okay, so we would say that the domain of g of xy is the closed disk centered at 0, 0 with a radius of 3. All those points can be plugged into the function. Okay, now what we need to do is figure out what the range is. Okay, cool. So let's look at a point like right here. Let's call this point x naught, y naught. Okay, what can we say about this point x naught, y naught? Given where I've drawn it, like on the edge of the disk. What do we know about it? What can we say about that point? What do we know about it? Like this point x naught and y naught. Like there's something, if you were to look at that x naught and y naught and like say another point over here also on the edge of the disk called x1, y1, they're obviously not the same point, but there's something very similar about the two of them. Okay, cool. That's true, but let me put another pair over here called x2, y2. I say that all three of these points have something very similar in common to each other. Yeah, yes, exactly. We know that x naught squared plus y naught squared equals what? Well, yeah, what is our r naught in this case? Yeah, which is 9. There we go. Cool. So using this fact, let's see what happens when we plug x naught, y naught into g of x. Okay, so if you plug it in, you're going to get the square root of 9 minus x naught squared minus y naught squared. Okay. Now looking at this, you can notice that I can factor out a negative from both of them, which would give me 9 minus, factor out the minus, x naught squared plus y naught squared. And what do we know that x naught squared plus y naught squared is equal to? It's equal to 9. Which means that we get the square root of 0, which is 0. Okay, now, is it possible for g of x comma y to output a number smaller than 0? Is that possible? Like here, we plugged in a value from the edge. When you plug in a value from the edge, you get 0. Is it possible that you could find another number to plug in that will be smaller, or another point, my bad, that you could plug into this function and it would spit out, say, a negative number? Is this possible? Okay, why not? Well, actually it has nothing to do with that. The function g of x, what does it do to your point? Like, ultimately, what's the last operation that happens? If you look at g of x, it does 9 minus the x component squared plus the y component squared, and then it takes the square root. Is it ever possible to get a negative output from a square root? No. So in other words, 0 is the smallest number in the range. It's just facts because of because g of x takes the square root of stuff, you're never going to get a negative number. Okay, so we now know that this is the minimum value. Okay, so this is sort of weird. G of x achieves its minimum around this circumference. Because if you take a point on the circumference, you're going to get 0. Any point on that circumference we just showed, or the edge, or whatever the hell you want to call it, it's called the boundary. Any point on this boundary of the disk will give you 0. Okay. Now, let's look at this over here. Okay, g of x is the square root of 9 minus x squared plus y squared. So now the question is, how do you make this as big as possible? Okay, and you notice that there are two components. You have 9 minus whatever the hell this is. So if you want to make this thing bigger, you should subtract something smaller. Does that sort of make sense? Like, if you want to... Okay, why is it not letting me type over here? Oh, okay, 1 second. What the hell? Okay, so how do you make this as big as possible? Well, you can make this larger by subtracting something smaller. In other words, you want x squared plus y squared to be small. What numbers can you plug in for x and y to make x squared and y squared as small as possible, so that you subtract as little as possible? Yes. So if you're subtracting 0, then x squared plus y squared equals 0. So in other words, what are x and y equal to? So if you're subtracting 0, that means x squared plus y squared would be equal to 0. What do x and y? Oh shit, I already wrote it. I'm so stupid. My bad. So if you want to subtract as little as possible, x squared plus y squared has to be equal to 0, which means x is 0 and y is 0. So in other words, where in the domain do you achieve your maximum, apparently? What's the point where my function is as big as possible? And I guess I'll point out when it will be when you have 9 minus 0, which means that you get the square root of 9, which gives you 3. Where is g of xy equal to 3? When x equals 0 and y equals 0. That is my maximum. Okay, so what this tells you, you have your maximum right here at 0, 0, and g of 0, 0 equals 3. Okay, so on the edge, if you take any point on the edge, you plug it into the function, you get 0. As you move into the center, you plug in numbers, they get bigger and bigger, and you max out at the origin. If you plug in the origin into the function, you take that point, you put it into the function g, it spits out the number 3. So my range, the range of g of xy is the interval 0 to 3. So in other words, this function spits out numbers between 0 and 3. Yeah, so the max is at the origin. So I'm going to pause here to see if there are questions. Do we have the questions? Vous avez des questions? Or avez-vous? N'est pas? Okay. Can I move away from this and talk about something else now? Or should I pause a moment? Who here's paying attention? Let's get some reactions. Curious. Okay, so we got 2 people, 3 people, 4 people, 5 people, 6 people. Oh, there we go, 7. Okay, there we go. Okay, cool. Just making sure. Okay, so we'll move on then. Okay, let's talk about graphing these bad boys. Let's talk about graphing functions of several variables. Okay, or of 2 variables. Because we're looking at stuff that takes you from the plane to... Okay, so... Okay, so I guess we should start by saying that the graph of a function of 2 variables is called a surface. Okay, and the way it works is like this. So let's like set up our axes here. Okay, so here's our z-axis. Here's our y-axis. And here's our x-axis. So you have this function g of x comma y equals z. Okay, now the domain is in the xy plane. So you can imagine here is my xy plane. Let's set this up nice and good so you can see it. Okay, and then we're going to draw in the xy plane some region D. Let's say that's the domain of our function. Actually, let's just make this very circly. Let's not squiggle it. Okay, so we're just going to draw it like this. So I've got this like circle in the xy plane. Okay, so what happens is you take a point in this domain, like right here. Okay, that's my x comma y. And you're going to plug that into your function. Okay, now what does the function spit out when you plug that point into the plane? Like, what does it end up giving you? Nope. So if you look at the definition of the function right here, you plug a point into the function, what does it literally spit out? You don't know what this function does, but if you plug x and y into g, what does it spit out? Yeah, cool, awesome. So remember, g takes as an input a point in the plane and outputs a point on the number line, specifically on the z-axis. So really what you can think of this as is z is the height of this function at the point x comma y. So what happens is that x comma y, oops, it gives you some height. Does everyone see how I drew this line segment right there? The height of that line segment right there is my z value. And you can keep doing this for all of the other points. Maybe at this point right here, the height or the z value is smaller. And maybe at this point right here, maybe the height or the z value is even smaller. So what you do is you get this shape. Okay, so I'm like drawing like, well, what happens? And maybe as you go around, it gets bigger again. And it even gets bigger over here. And maybe it even gets bigger over here. And maybe it ends up looking something like this. Just like making it up. I drew that really poorly. Okay, so what I've done here is I've taken a bunch of different points on that edge, I plugged them into my function, I'm just making this up, and each point gives me a different height. Okay, and let's say that we connect all these points. We get a surface. The graph will be a surface, and I'm going to say that, let's say the surface looks something like this. Actually, we should probably do this in green. Or no, let's do it in white. Oh my god, I'm having like a hard time drawing this. It's so much harder because I can't, like as I draw, it's like different than drawing on paper. I can't, like where my hand is drawing is like literally not on the screen, so it's sort of hard to line it up. Okay, so does everyone see my surface there? I've got like, it looks like I took like a stick and I sliced it basically. That surface is the graph I would get. How do you get that surface? You choose a point on the disk in the XY plane, you plug it into your function that tells you how high up you go to draw your surface. Okay, so what you could do is you can imagine that you choose some random point, like right here on the, actually let's choose a different one. You choose a random point like right here on the plane, on the surface, and that came from some point down there on the plane. And the height between that point and the point on the plane directly beneath it is determined by G. That's just how it's drawn here. It might not always be a slice. Yeah, so what you do is you choose some point, right? X naught, Y naught. Okay, and then what you do is you plug that X naught, Y naught into G. That will give you some Z naught. So if you have your Y-axis, X-axis, Z-axis, you have some point X naught, comma, Y naught. That will be right here in the XY plane. Okay, I can't write today. X naught, Y naught. Now, let's say that when you plug X naught, Y naught into G and you get Z naught. That means how high up do you go from that point to get the point on the surface? So this point right here is X naught, Y naught, Z naught. the height of that point is z naught. Okay, so the x naught and the y naught tell you where you are in the plane that positions you at the point, and then the z naught tells you how high up you have to go. Okay, and then you could do that for some other point, x1, y1, right there. You find your point on the plane, and then you're going to get some height, z1, right? And then you collect all these dots up here, and then that gives you your surface. So let's do an example. Let's start off with something really easy. Graph f of x comma y equals x. There we go, that will be good. Okay. So let's start by drawing our axes. So here's our y-axis. Oops, shit, that's not right. I mean z-axis. Here's our positive y. And here's our positive x. So remember, this is your negative x-axis. And this is your negative y-axis. And I guess I should point out that this down here is your negative z-axis. Okay. So, you take a point on the plane, and how do you determine the height of this function? What is the only thing that the height depends upon? No, the z is the height. So remember. Right, but in this, so we know that f of xy equals z, but my question is, what is the formula for z? Z is only depends on what for this particular function? There we go, yes. So basically, if you look at the x-coordinate, that will tell you how high up you go. So, here at the y-axis, what is the x value equal to? At the y-axis, what is x equal to? Always. So at the y-axis, what is x equal to? Yes. Which means if you choose any point on the y-axis, how high up from the y-axis do you go? Yes. So you get this line. Okay. What about when x equals 1? When x equals 1, if you take any point on that line at x equals 1, how high up is your graph going to go? Yes. So in other words, at this point right here, you would go up 1. You would go up 1. So this one was at 0, and now you're going to go up 1. This was at 0, and now you're going to go up 1. This was at 0, and then you're going to go up 1. And so on. Okay, at x equals 2. Oops, shit, wrong color. Yeah, we're gonna see that in a moment. So at this line, x equals 2, we now know that the height goes on the x-axis, you go up by 2. So what you can imagine is that you have all these lines going up like this. And yes, you get this like flat surface that like slowly goes up like so. Okay, and then you go the other way, it's going to go down, right? It's going to go under because the x values are negative under here, so they would be under the xy plane. So what you get is this flat slice that would travel like that. So let me show you how to do this on Mathematica. It might help visualize. It's a little hard to draw these things. Okay, my Mathematica's not showing up. What the fuck? Okay, this is bullshit. There we go. Okay, so we are going to do a parametric plot 3D. Oh. Sorry, I want plot 3D, not parametric plot 3D. Okay, so the way this is going to work is that to graph this, you need to give it your f of xyz. So what was f of xyz equal to? Just x. Okay, then you need to give it some x and y values. So we're going to have it graph from x equals -5 to +5, and y goes from -5 to +5. Okay, then there you go. You can see that flat plane I was talking about. So you have to remember like how this works. So let me sort of like move it around. Okay. Oops. So you have the x and y. Actually, let me change how I'm going to share the screen. Let me share the screen. Okay. So I'm going to annotate on this. Okay. So does everyone see this axis right here? Do you see how 0 is right there? And then 5 is over here. So if you find that point right there, you can see that what is the z value, right? Because this is this here is the z. Oops. This here is the z-axis. Okay, which means, and if you look at this right here, that line, you get a line. That means that this is your x-axis, because when x equals 0 right here, what is the z value equal to? 0. And if you choose like a point right here, that's also x equals 0. You look at that point right there, that also has a z value of 0. So that means that this is the y-axis. And you can see that if you choose a particular y value, if you choose a particular x value, the lines that go like this, you can see that they're all flat. Okay, so what needs to go right here is always your f of x comma y. Okay, then you need to specify the range for x and y on the x and y plane, what you want to see. So do you see how you get this xy plane right here? Okay, and then what happens is you choose a point. Let's change the color. You choose a point on the xy plane. This point seems to be something like I don't know, 3, 1. And then what happens is Wolfram then figures out the height. So if you look at 3, 1, what is f of 3, 1 going to be? for this function. So what is that going to be equal to? For this function, what is f of 3 comma 1 going to have to be? I guess let's start by asking you, what was f of xy equal to? Yes. Which means if you get this point right here, the length of that line segment up to that point on the plane is 3. And if you like worked on it, you could actually see that, yes, that seems to be a height of 3 on the z-axis. You can draw the little lines and you can see it. Okay, so Wolfram is actually really nice because it allows you to like rotate the drawing around. It makes life a lot easier. You can sort of like look around, you can see like, yeah, you get this slice like that. So let's make this more complicated. Let's do x plus 3y. Now you can see that it's this plane, but it's like tilted a little because now it depends upon the x and the y value. Okay, what do you think I'm going to get if I put x squared? Like, what shape should we end up getting in our surface? If I put x squared, let's guess before we actually do it. It'll be some sort of parabola, yes. But do you remember how, like, when we had x, the height was just determined by the x value? So do you see how, again, the height is going to be just determined by the x value? So it's going to be this weird looking parabola. It's a sheet of paper that's been folded. Because the way it curves only depends upon moving along the x-axis. Which means we know that this is the x-axis. Right, so if you like choose like a line right here, that's going to put you somewhere on the graph like that. Okay, we know that this is the y-axis, because if you choose a line going parallel to the y-axis, do you see how everything is at the same height? If you choose like a line right here. Hopefully you can sort of see that. Do you see how if I chose a line parallel to the y-axis, like the height remains the same? Okay, so what happens if I put x squared plus y squared? You're not going to get a folded sheet of paper anymore. You actually get like, it's folded in two directions because as you move around the x and the y-axis, it's going to be curved. Okay, so you can like see all sorts of cool stuff. Let's put that original function that we had earlier. Do you remember how we had the square root of 9 minus x squared minus y squared? You get this like dome looking thing. And if you look at it from above, on the xy plane, the domain is that circle, the disk, right? Does everyone see the disk? As I'm looking at it from above, you can see that we took points from the disk. Alright. So let's end the share. I think we're going to end here today. So I'm going to click stop recording.